So in 3.1, 3.2, and 3.3, we started learning about parallel lines, or really lines and transversals and their relationship. Then we focused on parallel lines specifically, and now we're going to focus on perpendicular lines. So first of all, whenever you're trying to find the distance from a point to a line, we definitely have to find the length of the perpendicular segment from the point to the line. In other words, if I'm trying to find how far point A is from line K, well, if you think about it, I could draw a line from here to here. This is going to have its unique length, right? From here to here is going to have another length. And notice that, obviously the further away from point A I go, if I go all the way to here, it's going to have another length. And all those lengths are going to be different. So in an effort to find a consistent length between a point to a line, we concluded that the length is a line that hits from the point to the line that is perpendicular. Remember that things that are perpendicular lines intersect at right angles. And what they mean by at right angles is 90 degrees, right? And so, in fact, the shortest distance between the point and a line is going to be a perpendicular line. And so that is going to be the way that we are going to always measure a line. We're going to find a point, draw a perpendicular line to another point, and that length is going to be the proper length that we're going to use. So when we ask you to find the distance from point A to line BD, we know that we're going to have to use a line that is perpendicular to line BD. So if I come to the drawing, the distance from A to line BD, let me kind of figure out what that is. So here's point A, and here is line segment BD, like that, okay? So I have 3 lines there to look at, but if you notice, only one line is perpendicular. So this red line is the only perpendicular line there, and so that red line is going to be the distance between the point and the line. The other 2 lines, we are not going to use those because they are not, yes, they are lines, but they're not the line that's going to represent the distance. So again, how do you use the distance formula? Remember, the distance formula, or the distance between point A and point C, AC, right, is going to be x2 minus x1 squared plus y2 minus y1 squared. And so remember that I don't worry too much about y1 and x1 and all that. I just basically put point A is negative 3, 3, and point C is 1, negative 1. And remember that I always do top minus bottom. So I know the distance, or the length of AC, is going to be the square root of the top x minus the bottom x squared plus the top y minus the bottom y. And by top and squared. And by top and bottom, I just mean top of how I wrote them. It's not about the picture. It's just I wrote A, then I wrote C underneath, and so it's going to be the top one minus the bottom one there. So again, now it's just mathematics and making sure I don't make any computational errors. Negative 2 squared. Here, minus a negative is the same as plus a positive, so I have 4 squared. This is negative 4 squared is 16. Positive 4 squared is 16. So this is the square root of 32. So I know the length of AC is the square root of 32. And if I let you use a calculator, you would plug it in and you would get some number between 5 and 6. Because we're probably not going to let you use a calculator, I'm going to want you to simplify this radical. And I know the square root of 32. I know 32 is 16 times 2, and 16 has a square root, which is 4, so I take it out, and it leaves 2. So the length of AC is 4 times the square root of 2 units long. I don't know what the units are, but whatever they are, feet, meters, inches, whatever. So now we come over to here and we learn about perpendicular bisectors. So the perpendicular bisector of a line segment PQ. So notice we're starting with line segment PQ, and we're talking about the perpendicular bisector. So the perpendicular bisector of it is line N with the following two properties. So what does a perpendicular bisector have to have? Well, it's in the name, okay? In other words, line N must be perpendicular to line PQ, and it is. Check. And the second thing is N must pass through the midpoint of PQ, which is point M. And of course, because remember, to bisect something, you split it in half. Well, the midpoint is the exact middle of the thing. So everything to the left of the midpoint is going to be equal to the right. So both things have to happen. Notice in this, we show you that it's perpendicular with the little square there, and we show you that it's a midpoint, or it crosses at the midpoint, when we show you that these two segments are congruent. So check. So how can we, we're going to have some theorems, right, about perpendicular lines, and then we're going to have to actually prove them. So the first one is linear pair perpendicular theorem. So this is another new theorem. It says, if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So what this is saying is that if line G intersects line H, and the angles that are formed are equal or congruent to each other, angle 1 equals angle 2, then line G and line H must be perpendicular to each other. There's only one pair of angles in a linear pair that are congruent, and it's when it's 90 and 90. And so it has to be right angles for that to happen, okay? And so, again, that's all this theorem says. So if angle 1 is congruent to angle 2, then line G is perpendicular to line H. And again, this is the symbol for perpendicular. Okay. The perpendicular transversal theorem, here's another one. It says that in a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. So again, we start here with our two parallel lines. And basically what this theorem says is that if line J is perpendicular to one of the lines, then it's perpendicular to the other. Okay. So that makes sense. Remember that corresponding angles have to be congruent. So if this one's 90, this one must be 90 as well, because we know these lines are parallel. So it makes common sense that this theorem would work, but again, we write it out. So if H is parallel to K and J is perpendicular to H, then J is also perpendicular to K. Couple more theorems here. Lines perpendicular to a transversal theorem. Here it says, in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So this kind of is a little bit opposite of the one before. The slide before told us that if these lines were parallel and this transversal was perpendicular to one, it's perpendicular to the other. This one happens to tell you, well, what if you don't know the lines are parallel, but you have this transversal here that happens to be perpendicular to both lines? Well, once you see it's perpendicular to both, then you can conclude that the lines are parallel to each other. So in the last slide, you knew they were parallel and you concluded that one of the angles was perpendicular. Here, you know that both angles are perpendicular and you conclude that the lines are parallel. So what you really need to be know is, what are you trying to prove? Depending on what you're trying to prove, that's the theorem you're going to have to use for that. Lines perpendicular to a transversal theorem. And then we come again to another problem here, and it says the photo shows the layout of a neighborhood. Determine which lines, if any, must be parallel in the diagram. Explain your reasoning. So here, you're trying to prove parallel lines. Okay? So, let's see. What have we been given? Notice that we have here these red lines and we have our transversals. But if you notice, this one's perpendicular over here, and this one's perpendicular over here. So both of these angles are perpendicular. And so by seeing that, I know that this line here must be parallel to that line. Okay? None of the others, oh no, that's not true. So I know that those two lines are parallel because of those perpendicular angles. And then I also notice that this is perpendicular and this is perpendicular. And so these two help to tell me that this line is parallel to this one. Theorem-wise, the theorem I use is perpendicular lines to a transversal theorem, which came up on just the previous slide, okay? Because that theorem proves lines are parallel. In a proof, you could just tell me again, if two lines are perpendicular to the same line, then those two lines must be parallel. You could kind of tell me the theorem in the proof and I'll accept it because again, I know that these become a tongue twister, but definitely know how to differentiate the different things.